Thank you very much for the invitation, the opportunity to be here and to be back here. A little bit of my personal history. I have been for quite some time an observer member of the CCU, as I have been General Secretary of the Commission Internationale de l'Éclairage, the CIE, who has a memorandum of understanding with BIPM, and because we were really realizing the Candela. So I'm happy to be back here. So, and this, of course, to tell you, well, I know a little bit about, I'm not a metrologist, I'm a business person with a training in data science. So I have a background in software development and data science. And basically, I'm looking to things from an industry perspective. Very much. So I'm currently the co-convener of this Joint Working Group 6. Why is it a joint working group? Well, Subcommittee 42 is the committee within the ISO and IEC world, which is standardizing artificial intelligence. I will not dive too deep into that, but it might be worthwhile because many things which Cornelia Benz just mentioned are covered in our technical committee and are covered in our working group. So we have standards on that, like for definitions, for instance. And we have standards for assessing robustness. We start currently a work to assess functional correctness. And this I will dive a bit deeper. So it's co-convening because the partner is CASCO, ISO CASCO. So the Conformity Assessment Policy Committee of the ISO, which you're aware. So we are really forming what we are doing is to try to have an application, a sectorial application of CASCO standards. So, and the second I'm convening is the IEC Task Force AI. The IEC, you might be aware that the IEC as partner organization of the ISO has conformity assessment schemes itself. The IEC is one of those. And there I'm convening this task force on how to see a very practical application, how to apply existing standards and link them to the sectors, because this is one of the major challenges we have, that all of us, metrology and Subcommittee 42 and ISO IEC, we're writing sort of, not always, but we're writing very often horizontal standards and using horizontal methodologies. But in particular with technologies like artificial intelligence, which is so highly context dependent, it is very important to look at the sectors. So that said, this gives you a little bit, will start to setting the scene. I will do it very, very quickly, but just to be on the safe side, because we always say it is about certification of AI and there's a lot of schemes there. The question is, in which context are they? Therefore, just some slides, just a few sentences in which context we are. I know you're aware of it, but it's a story to tell, right? So then what are we doing in ISO and IEC JTC 1 Subcommittee 40? What are we doing in the group? I have the honor to co-convene, and which project we currently have. And then I looked around in the VIM, to be very honest, in the GUM, and I did some semantic exercises. But this is a question, and I really invite, and I'm happy, and I will be here during the coming days too, to start to continue a conversation, because it is important. The questions I will ask you are very open questions where we do not have an answer in industry, in many parts of academia, and in the standardization world. So long story short, so we are basically, and this is the important because this is a real trigger, ISO and IEC are the technical standards organizations of the World Trade Organization, which are recognized, which are the ones who follow the 6 principles of standardization. So we are those who moved, of course. I don't always have to tell you that BIPM is one of the major promoters of international trade, but I'm now really focusing on the ISO and IEC. So we are the standardizers who have the task to remove technical barriers to trade. So what we and the ISO CASCO is the policy committee who writes the standards, the process standard. You're aware of those 17025, for instance, which is the basic standard for testing and calibration labs, or 17065 for product certification, etc. So this is the major trigger, and this is the major lever we have because we are providing standards in a framework and a very well set, even though it is challenged, as we all know now, in a more than ever fragmented world, or again, not ever, but again fragmented world, but still it exists. So we have mandatory technical regulations in our countries and our regions and in the world trade framework. And then standards are always voluntary. So you can have them in procurement, you can take them over in governments, and then you have in between, you have conformity assessment, which uses this international standards. So here I just showed here that we are on these three building blocks in the QI, from regulation, by measurement, documentary standards, claims, accreditation, etc. We are here now in my presentation in the blocks 2, 3, and 4. So measurement, documentary standards, and the claims of, and I did it a little bit, not a clear drawn line, because why? We are still on a developing road, and this is to show you why. So this is the standards I will refer to, the so-called Casco toolbox, starting from the definitions. All definitions taken from conformity assessment are taken from this fundamental, just as a reference, because I did not put it everywhere then. And this is the normative level system as we know it. Accreditation was already mentioned, and this is even taken from it's a figure which is used very often from the German accreditation organization. I use it because I like it, and it's based on the European accreditation MLA. And it shows very well in which levels we are, because what they do is the accreditation has a very clear set framework of which standards apply to which level. So at the level 5, we define the requirements for the objects of assessment. So basically what we would call the technical standards. In the level 4, we then provide already the building blocks of conformity assessment schemes or conformity assessment methods to apply these standards or to assess the conformity of those requirements in the standards. And what we are doing in ISO and IEC right now is in that level. So it's a high level framework. We have test-based methods. We have test methods too, to dive deeper into that. My colleague who is today was not available today, who is chairing the task force, the joint working group on testing. So, and this is basically the governance structure, etc. So this is what ISO and IEC JTC 1 subcommittee 42 is doing. I provide it here on the right and the left side. I'm trying to go there. It can't anyway. It is a living link, so you can just click on it and there you'll see all the standards. We're currently working on 43 standards. So, and we have published quite some. We have about 64 members, and there is a huge and rising interest, as you might imagine. There is a lot of budget and investment going into artificial intelligence currently. What we are trying to do in subcommittee 42 is to be to really provide a horizontal ecosystem framework, and of course to interlock with the sectors. We have joint working groups, like with conformity assessment. We have it too with health informatics, like with ISO TC 215, or we have it in functional safety, so with the IEC TC 65. So what we're trying now to do after this, the fundamental standards, some of those are settled. So we're really trying to connect ourselves to the sectors themselves. So that said, is a real invitation to the metrological community, not a sector, but really to bring in your know-how into these standardization, because these standards are used in procurement. These standards in subcommittee 42, they are used in sectors. So it would be really, again, we don't have so many, we just have 1 or 2 people coming from the metrological community within this work, but which is driving world trade. So in artificial intelligence, so many standards of subcommittee 42 are taken into the standards body, for instance, of Sense and Elec, so the European one, or taken in other regions into the national standards repository. So a huge invitation, please provide your know-how. So Peter, how long do I have, by the way?
15 minutes.
15 minutes left. Okay, good, thank you. So, but I will have time for discussion too, of course. So I try to be done in 7 minutes. So this is the framework we have. I just want to remind you what the definition of conformity assessment is. It's demonstration that specified requirements are fulfilled. So a specified requirement is a need or expectation that is stated. It should be in normative documents. So, and last but not least, we have the object of conformity assessment, which is the entity to which specified requirements apply. And this is, I just reminded you of these definitions because those are the ones we apply and we are struggling with. So an AI system, what's that? This is the definition which is laid down, and here you have it. It's really downloadable. It's the framework standards. It's the artificial intelligence concepts and terminology, freely downloadable from the website. Again, this is a living link. You can just download it for free. So, and this is a very important thing to say. The ISO and IEC is consensus-based. So there might be 20, 50 definitions of AI, but in international standardization, as in metrology, we need to be comparable. So we have to have one consensus, which sometimes is a very minimal consensus, but we have to find a consensus. We are consensus-based. This is one of the major principles of the World Trade Organization for standardization. So, and this is for the time being, this is the international definitions we are using. It's an engineered AI system, is an engineered system that generates outputs such as content, forecasts, recommendations, or decisions for a given set of human-defined objectives. So we still have the human in here because we humans, we define objectives and related tasks, etc. And it can use various techniques and approaches related to artificial intelligence, and with varying level of automation. And you see here, for instance, one very important difference. Very often we're talking, or it is talked about autonomy. We don't talk about autonomy. We talk about automation because this is the concept we're applying. Autonomy would mean that you take the human out of the loop. So, and this is very important. This is very important to say, to talk about automation. It's the same in when we're talking about the self-driving cars, right? So we have automation levels. So what are the framework conditions we have? And Mrs. Dance, you already mentioned one very important of those. AI and its application is context dependent. It is highly context dependent. It depends on the use, it depends on the objectives, it depends on the tasks of the system, and it depends, of course, on the data it was trained with. So to have standards and say the silver bullet does not exist. We have a lot of silver bullets, or at least some bullets, but we try to find it, but there is no one silver bullet. And this is a real challenge. Which will never be solved because the application areas are potentially endless. I'm sure there's a mathematical equation formula, etc. for that, why they are not endless. But I'm using this concept of endless. Just say that there is no, you cannot just say we are assessing AI systems. You always need the context. So, and there I'm already started with contextualizing AI systems. One of the context is stakeholders. Who are our stakeholders? For instance, in regulations, it's the regulator. The regulator wants something very specific. In some other products, it's the consumer, or it's the person or the organization who writes the procurement. And depending on these stakeholder requirements, the AI technology will already be different and has to be different. So we have, and therefore it's difficult to get it, it is a moving target. It is highly context dependent. And then we have different technologies. AI, artificial intelligence, is not one technology. It's a huge set of technologies. Currently, it's the hype, it's LLMs. Everybody's talking about LLMs, but the LLMs, they're not there. It's not only, I mean, it is there, but they are maybe the most complicated. And I called my I called my talk, I tried to have a little bit provocative, I called it Taming Conformity Assessment, Taming the Stochastic Parrot. There is a nice coined term calling LLM stochastic parrots. Why? Because they are guessing what are they doing, they are guessing the next word. So giving them reasoning, if we would, as humans, would behave like that, it would be an interesting output and communicate. Well, they are quicker, of course, than we are. But at the same time, it is not about really concepts, but it's a guesswork. In standardization, we call artificial intelligence statistics on steroids. Therefore, for instance, we are not so happy with anthropogenic words like anthropomorphic words like hallucination. They don't hallucinate, they just guess wrong. So there's not something they're doing, because hallucination, it's a process, a complicated process which happens in the brain, but they don't hallucinate. They just guess. So maybe we sometimes hallucinate too if we're just guessing, but this is very important to know. So then the next one is defining the object of conformity assessment. So is it the AI system? Is it several AI systems together? Is it related to a management system, to a quality management system, to a process? Is it related to a product which has several AI products enabled in it? What is it? To really define the object of conformity assessment and to define its dependencies. It's a real challenge to do that. The requirements are not complete. The question is open, can they be ever complete? And we have diverse legal environments, etc. So what we see here, what we have to, and we have, of course, the issue in our society still with resources and knowledge. So we try to build trust in a complex environment, but for that we have to be aware that we are in the world where we have a complex, where we have complex contexts to understand and to define. And there, I think, this is a real challenge for metrology. So we have different, these all sound, it's context dependent, and we have diverging definitions, of course. This is an international definition I presented with you, but for instance, a regulator like the European Union, European Commission uses another one. Then, and this is a major issue, then we have the risk definition. The risk definition is according to 31,000, which we are using in subcommittee 42, which is the effect of uncertainty. So it's an organizational risk. Whereas in the product safety sectors and the sectors, for instance, like medical devices, risk means the combination of the probability of an occurrence of harm and the severity of the harm. So you're combining a lot of probabilities already in there and assumptions, but it's not the effect of an uncertainty. So, and if you're using a risk-based approach, this becomes rather important. And in standardization and in testing and in conformity assessment, we are using a risk-based approach. So these are the major two projects. The one project is the high-level framework and guidance for the development of conformity assessment schemes for AI system. It is really about schemes. What and how shall, if you're a scheme owner, what and how shall you, do you have to consider to deploy a conformity assessment scheme which has AI systems as an object of conformity assessment to the market? We are following, we have two challenges. First, the context we are working in. Second, that we have another moving target which is 17067, which is currently completely reviewed. And it's currently in this stage, moving now to FTs, so it will be published potentially next year. But we are aligning with that standards, which is the fundamental of conformity assessment schemes. So we're aligning with that one, plus other documents like IAF documents, etc. This is one point. So we try really to find to combine a variety of like processes, products, etc. in a scheme for scheme owners. So if you would be a scheme owner, this is the standard for you. The other is the task force AI and digital transformation and the IEC, which is conformity assessment system operating under 17025, so the testing and calibration, and 17065, the product certification. So if we're looking into that, AI system as an object of conformity assessment can include a variety of requirements. It can include management system requirements. It can include competence requirements. We are they're in their committee draft, so in a rather early stage. That means I cannot provide you with the table of contents because it's copyright protected, but this is the way to go. So we invite you, as said, it's an ISO Casco joint working group, to participate, if possible, for you to participate in there while you are ISO or IEC national member body. So we can do both, either management or to combine it together, and management system certification and product certification. The management system is 42, could be 42,001, doesn't have to be. We consider the lowest level of assurance because it's on the organizational level. Then the 4206 is the requirements for bodies providing audit and certification of artificial intelligence management systems. This was written for the conformity assessment bodies. And of course, product certification shall be used for manifold schemes. What we are providing, combining it with processes such as the AI management system. So it should be, at the end of the day, well-structured combination of conformity assessment activities, including the auditing of the management system part. In the ICE, it's a different animal again. We have, in conformity assessment, we have decided to look into the medical device sector, because there we are in product certification, and we are in electrical safety and in the safety certification and testing. So the advantage of that is looking into medical devices. It's a highly regulated sector, and the disadvantage is it is a highly regulated sector. So why do we say that? For emerging technologies, this is not a real experimental field. At the same time, for emerging technologies, a fantastic experimental field, because they have they have already in the sector, they have a mature quality management system where you have data representation, characterization included. We have a risk assessment, which is based on the product safety risk, not on the organizational risk. And we find the clash sector-specific versus horizontal standards. We are not yet there. We are currently developing this process together with the sector, so with the medical device industry and the regulators worldwide. It's IEC JTC 62. The potential solution is that we would include only specific aspects of horizontal standards into the sector-specific ones. And we assess the input and the output, because this is what we can see, right? You already mentioned the term black box. The system is a black box. So, this is a potential solution. As said, not yet there. We are happy to receive inputs, questions, challenges, sparings, etc. So, last but not least, here the AI quality model. There were some features already mentioned. In 25 or 59, in the standards, you have these are called AI quality model with all the characteristics and attributes of an AI quality model. It's derived from the software engineering world. Yeah. In metrology, I know. I'm looking, let's just quickly look into functional correctness. So I will leave out the metrological part then. No, I shall not leave it out, so no. Functional correctness. I took functional correctness. There is currently work in the standard in developed, how to assess functional correctness. This is one of this is basically in the view of our community, the most important one. And it says a degree to which a product or system provides the correct results with the needed degree of precision. Well, you already have something what you're using in metrology, you have in there. But the interesting thing is, of course, 2 times the term degree. So when it comes there, it starts, again, it's the standard 25 or 59 software engineering, the AI quality model. And currently we are working on the model relating it to existing metrics we already have. So here we are. We start small, right? We have a definition, and we want correct results. But what are those? What are the correct results? And we want to have it with the needed degree of precision. And we have again, and this should be there's a degree to which a product or system provides us with these correct results, with the needed degree of precision. And the correct results is, who decided on what is correct? Just remind you back to what I said before, that we have the stakeholders, for instance. It might be different. In metrology, it might be different than in industry, for instance, or for regulators. Who decided on what is correct? And who calibrated and labeled? Calibration, my colleague comes to that, Thomas Doms comes to that later. Calibration in machine learning means completely something else than in metrology. So, but we're using that. It's, again, the terms of uncertainty is the same. It's different. So needed means the objective task, domain, and application. Without a domain and application which is properly described, like for instance, we have ODDs and automated driving, without a domain and application which is properly described, narrow enough described, we cannot define what is needed. It's needed, what is needed is in the objective and tasks of the system, and it's context dependent. So from that, we choose the metrics and the prioritization. It is not only about metrics themselves, but how we prioritize those. It's context dependent again, and use case dependent. So AI systems do not usually provide functional correctness because a certain error rate is expected in their outputs. It's a funny thing for metrology, right? You just say not only it's an uncertainty, but you expect an error. Therefore, it is necessary to measure correctness, incorrectness carefully. And then we have the trade-off because functional correctness and robustness, they are interlinked. But if you have high functional correctness, so high what you would consider correct results, you might lose the robustness of the system. So again, we have to think of trade-offs we have of properties which are related to each other. And here I advise to the standard 421192, which is testing of AI, which is risk-based testing. And I'm skipping. These are the standards in here. You have the presentation, but I'm not skipping because I just wanted to show you my exercise. I did the exercise, I went to the VIM, and of course, what did I use? Traceability, metrological traceability. And what I did is I substituted the terms by their definitions. And I did that because just to see an overview and to get a sort of an idea of what metrology is talking about when you're talking about metrological traceability and how that could relate to machine learning. You have there a lot of quantity values. You have reference, you have an unbroken chain of operations that under specified conditions in a first step establishes a relation between the quantity values with measurement uncertainties. I gave it an up with measurement uncertainties because it was about 5 times it would have been in that definition again. So it seems to be an important concept. The other important concept I found is the truth concept. It's in the VIM, you have it 55 times. So truth, and then the question is, of course, what is truth in machine learning? So how can the definition of metrological traceability be applied to data which form the reference of an AI model? Is this, it's a reference material, reference standard? How do you do that? How to deal with stochastic and constantly changing systems in metrology as defined in VIM and GUN? How to calculate the measurement uncertainty, budget of an AI system or systems which might be used together or in an unbroken chain of calibrations. How do you decide if the measurement uncertainty is too high to achieve metrological traceability? It's really open questions to you. Huh? And how do you document an unbroken chain of calibrations if you're using several devices having ML components and are trained on non-standardized data? And by that, I have here some more thoughts and questions. Is metrology a fixed framework or a competence concept? Because currently, as you see it in the VIM, it's a fixed framework. It's always about SI units, traceability, reference, etc. So is it a concept? Is it a competence? Or is it a fixed framework? If it's not a fixed framework, but a competence, how would you apply it in a machine learning world without losing your major framework? So, and what is the reference data and the truth in machine learning systems? If each prompt provides a different result, how do you ensure their compatibility?
Okay, thanks for inviting me. My name is Thomas Doms. I'm here in 2 positions and two functions, as Peter mentioned. So I'm the product owner of TÜV Austria's Trusted AI catalog, AI assessment catalog we developed in the last 6 years, and started the work as no real standards were available at that time for AI assurance. And apart from that, I'm also the work package lead in the AI Quality Infrastructure Consortium for the development of a comprehensive AI assurance framework. And I will give you some insights today in that work that we perform there in the AIQI, as well as what are the outcomes of our testing and assessing of AI systems and what are our basic concepts for that, and try to link it and laying a bridge to maybe the metrology domain as well. As Martina mentioned, and as you all know, if we are speaking about safety relevant AI systems, of course, we need a measurement-oriented assurance approach and testing approach, because AI cannot be based on general benchmark results or supplier claims. The behavior depends strongly on the data it sees, on the context and the operating conditions. As you all might know, static benchmark scores are not bound to the operating domain entirely. So performing and optimizing your system against some benchmark data sets is just misleading you, because the system might not be able to generalize for its functions and tasks enough. The performance can change in such a dynamic setup as an AI system is after deployment through updates or drifts, distribution shifts, model drifts, data drifts, domain drifts. There's a lot of possible impacting and influencing things that can happen to your system. And so we believe that we need some functional trustworthiness requirements that are clearly linked to the risks and the intended use of the system, objective metrics and acceptance criteria. And it's, of course, very important to have a valid monitoring of the system performance implemented after deploying the system throughout the entire life cycle of the system. And what is one core part of assessing systems, and that is typically linked to your domain as well. We have to perform statistically valid tests to get evidence for the performance and the performance guarantees of the systems on independent test samples. And that links to the first part where we are thinking about these things as well. We started 1.5 years ago now in the AI Quality Infrastructure Consortium that was established then to building a common assurance foundation for AI. Who's part of this AIQI consortium? These are all the relevant actors in the quality infrastructure. And this is, of course, the metrology institutions like NPL, for example, being a member, the standardization organizations like ISO, CENELEC, the accreditation bodies like DAX, UCAS, and the Canadian ones, ANAP, and American ones, South Korea, India. So throughout the entire world, we have at the moment about 70 members. It's the TIC industry, so the testing, inspection, certification industry, with the via the TIC Council. That was the reason I was delegated for the work package lead there. And of course, also academia, because we want to see what is the state of the art given in existing and developing standards versus what is state of science. So what is the knowledge we have behind what might be the concepts of the future for testing and assessing and assuring AI systems. What we are doing there in our work is try to map the existing regulations worldwide. We have started with the AI Act and standards to the assurance tasks. We have a meta architecture coming from some German colleagues from the TÜV AI Lab, where we have researched and investigated about the existing assurance frameworks available outside there in the world, and what can be the merged framework architecture for our then comprehensive assurance framework. We think about how to interpret the general requirements given by standards, giving guidance about that, defining test resources that might be appropriate for measuring the fulfillment of the requirements. And of course, we also want to align within the different partners in the consortium about unified approaches for performing assessments. So from an accreditation and quality assurance perspective for assessments, as well as for performing the assessments as conformity assessments bodies. And of course, at the end, it's all about, as Martina mentioned, we want to implement better traceability from single requirements given by standards to the assurance implementation and the fulfillment built on metrics as well. As I mentioned, we started 6 years ago in a scientific collaboration with the Johannes Kepler University, the Machine Learning Institute of Sepp Hochreiter, and the Software Competence Center Hagenberg, which is an applied research center here in Austria, as TÜV Austria, to develop our own testing catalog. That was due to the reason we implemented first testing systems based on AI for ourselves, and these were implemented in safety critical environments. And we, of course, wanted to have established as well performance guarantees for these systems that we use for our own testing purposes. And there were no standards available, so we invented a test catalog for ourselves. It consists of about 400 criteria. It's lifecycle based, and it's focused on auditable and evidence-based AI assessments approach. And as you can see, we try to cover all the aspects here in an aggregated perspective and view, and throughout the life cycle from the inception phase and stage towards the model development to the deployment and operations, and updating and maintaining the system as well. What we believe should be the basic concept in the assurance process for AI systems is, of course, starting with a 5-step approach. It's defining quality requirements first and the corresponding thresholds for these quality requirements. So what are the requirements? What are the metrics to be measured? What is the outcome, the acceptable outcome for that? This is derived from the use case and typically risk-based. So performing a risk analysis is, of course, one of the major concepts. Then define how to measure these requirements. We call them minimum performance requirements for the AI systems and safety critical implementations. So define measurable properties and metrics. How can we evaluate then against these requirements? What are the appropriate tests with statistical validity? Of course, in just looking in the perspectives that we have providers and as well, so people developing, deploying, providing the systems, or also using the systems, we have to communicate the results. So by technical documentation, by user manuals and stuff like that. So what kind of evidence do we have? What is the intended purpose, the non-intended purpose for, and functions of the system? What are the limitations of the system to use it in a safe and secure way? And of course, also we focus on the maintenance of the system. So how can we continuously monitor the performance over time? And I will show you some concepts for that as well. So the basic principles of our catalog, and that is also linked to the work that Martina showed in her presentation, and the functional trustworthiness and functional correctness approach is, we call it functional trustworthiness principles and it starts with, we need a clear definition of the application domain, so of the operating domain, the ODD, as you might call it. So where and under which conditions is the AI intended to work. From that, we want to define and deduce minimum performance requirements. It's typically done, as I mentioned, via a risk assessment. We will see that on the next slide as well. It might be lead to other aspects we know from functional safety, like safety integrity levels for machines, or the automotive safety integrity levels, ASIL levels that you might know as well. And also performance guarantees maybe the users and customers are expecting from the systems. And the crucial part is then the step 3, verifying against these minimum performance requirements. So can the system achieve and guarantee this performance by statistically valid testing? Without these domain definition, minimum requirements, and valid test evidence, we believe that the assurance claims that can be given or will be given will remain too vague. And in a more technical perspective and view, so that are the steps that we expect from our customers in conformity assessments to perform. So defining the operational domain, performing a risk analysis, deriving from that matrix MPRs with a significance level that we expect, and then performing statistical tests on the trained model with the test set of independent test samples, and also for statistical correct tests, of course, the sample sizes, the period and retesting periods should be defined. And if the system then achieves the minimum performance guarantee requirements and fulfills them, we can issue a certificate. And this certificate, in our perspective, is bound not to a static certification period, but to the maintaining of the minimum performance guarantees during the usage of the system. So what do we measure in our approach? Of course, all the things that you would expect as metrology institutions. We are dealing with performance aspects, with robustness aspects, uncertainty, security, and operational reliability. And looking at time, I will focus in the next slides on some of the aspects, and Martina mentioned that as well. One of the central concepts in your work as metrology institutions is, of course, uncertainty. And uncertainty estimation is as well a key aspect, as we believe, for high-risk systems. But we have, coming from the machine learning domain, another definition, different definition for uncertainty, of course, than you might have in the metrological uncertainty definition. So it's about the doubt from machine learning perspectives associated with the model's prediction or decision due to data ambiguity, stochastic variability, or incomplete model knowledge. Martina mentioned that we typically are dealing with black box systems versus you are having an understanding of uncertainty that is related to a quantified degree of doubt associated with a measurement result and expressing a range of values that could reasonably be attributed to the measurement. And as you can see in the table, from the machine learning perspective, it's all about the object, the model itself. So about the decisions, the classifications, predictions, the tasks the model is performing. versus the measurement result. The main question is how reliable is the model output, and how likely can it be reproduced and be stable about time. The typical causes for uncertainty and a great variance in the decisions of a system and the output of a system is also according to our assessments, and there were some startups as well as big international companies who performed assessments via our testing catalog. It's often linked to limited training data, to synthetic data with the data quality issues behind, to distribution shift, model limitations, choosing the wrong model for the tasks, stuff like that. And of course, we have different expressions behind how to deal with uncertainty. It's about confidence, probability, predictive interval, and of course, which is the basic concept of uncertainty from a machine learning domain, expressed on the next slide, the epistemic versus the aleatoric uncertainty. Looking at that, why uncertainty matters, what uncertainty is usually consisting of the uncertainty in the machine learning domain consists of two parts. So aleatoric and epistemic certainty. The aleatoric uncertainty is focused on if the input is ambiguous or noisy, and the epistemic uncertainty more about the Model X knowledge in a region of the domain in which it is operating. And as we have seen that all these concepts and the known concepts for measuring aleatoric and epistemic uncertainty have pros and cons, and sometimes are a little bit restricted in what we need for high risk systems. We also invested in our scientific collaboration with the Johannes Kepler University and the Software Competence Center on some additional concepts that will be given in detail, and I would like to mention that here because we will run out of time. In the back up of my slides, so we developed a QAM concept, so quantification of adversarial models. So that is better to measure, is suitable to measure aleatoric uncertainty. And what we are investing and researching at the moment is what are the best concepts to evaluate and measure uncertainty for natural language processing models. And there is an approach which is under research at the moment that looks quite promising. And you will see more technical information in the backup of the slides, and the slides will be available via your SharePoint here for the organization. And another issue that I mentioned, and that Martina also mentioned, that is very important. In the past, we had more static conformity assessments procedures. So having a type approval for a physical system and the product, and inspecting the quality management, doing factory inspections on a regular basis, doing monitoring audits on a regular basis, that suits well to more static products or to software related products that are more developed in a classical way with deterministic approaches behind and logic behind. But with these probabilistic systems that during operations might have drifts or shifts in the distribution and behave in a not expected way, it's very important to have continuous monitoring implemented. And what is our approach for that? So the basic concept, as we saw, is we have these minimum performance requirements as long as they are met. And during the operations of the system, the certification can be maintained and upheld. What we have seen, and we also ask ourselves what was the best monitoring approach and retesting approach for the performance during operation. And one thing that looked quite promising is the family-wise error rate concept that we used. And the question was then measuring the family-wise error rate as a metric for that, for the fulfillment of the minimum performance guarantees. It's maybe comparable to having a budget available for your system, and you spend for the retesting some amount of your budget. And you can decide for yourself how many, for the retesting, how many, what quantity of your budget you would like to invest. The bigger the invest, the higher maybe the certainty of the result. But of course, then the retesting will reduce your budget in an increasing way, so that you will be led to a recertification very soon. We have then looked what can be the best multiple testing methods to implement these concepts, and we have looked from more static concepts that are often used in machine learning, like the alpha spanning, so online Bonferroni, through fixed sequence testing, to the ADIS spanning, which is the most adaptive approach that we saw. It's also the best methods, but it only works on independent hypotheses. And giving a use case and application domain, we have no independent hypothesis available. So the best method for certification retest is fallback procedure. And some additional information about that and the mathematical concept behind, I would not be able to explain because I'm not a machine learner. And the researcher for that is also given in the backup slides. And that leads to a continuous monitoring concept based on that fallback method, that we measure the significance level exhaustion about time for the models in use and the systems in use. And if the significance level is exhausted, then we have three options, and we prefer the option 3 then to reduce the efforts for the product owners. So option 1 will be full recertification, so hard reset, new model, new training and test data aligned with that. That could be one approach, might make sense in some circumstances. Option 2 could be a certification freeze, so the last certified model remains deployed, but no further updates are possible and no other changes are possible for that. But we believe that the option 3 will be the most pragmatical approach for that. So controlled rebaselining. The current certified model will be serving as a baseline. We will implement new training and test data on that, and we will have then an in-depth review of the updated model and the fulfillment of the minimum performance requirements of that. So looking at that and the time, we come to the key takeaways. So from our perspective, and that's absolutely aligned with your domain as well as in metrology institutions, safety relevant AI requires measurable and risk-based assurance, but we will not have, maybe as in the past, static metrics. We will have a more dynamic setup. The ground truth is, as we have seen for complex systems used in real and daily life, look at autonomous driving also, is not easy to define. So that will be a challenge for all of us. So maybe the risk-based approach with defined minimum performance metrics might be a bridge towards that. It's a question if you have labeled data that you can use for the metrics as well. That is also a challenge. We need more testable criteria, and to be honest, with our 400 criteria, of course, we have quantifiable criteria and quantitative criteria in our testing catalogs, but as well a lot of process-related and qualitative criteria as well. It is a good mixture from our experiences, but we are not satisfied, so we will invest for the next 8 years in a new established scientific setup, more on robustness and performance and safety guarantees of systems, and also based on generative models as well. Basic concepts from our understanding and belief is that we need the clear definition of the operating domain, the minimum requirements related to that as performance guarantees and statistically valid testing. And that's not easy to implement because also machine learners do not understand the correct concepts of statistically valid testings. It's more trial and error methods that we often see in the market there. Uncertainty and monitoring are essential for the life cycle validity, of course. And we try as in AIQI quality infrastructure and the TÜV Austria with our role there as conformity assessment body and doing research to contribute to a common AI assurance infrastructure. And we'll be glad if we maybe can uphold and have some additional discussions, maybe also after these workshops about the central concepts. And I would, of course, then integrate our experts and scientific researchers as well. And we started some of these discussions as in the past with NPL and PTB. So maybe there are more of you interested in that.
So just very quickly to my background. So I'm a mathematician and data scientist. leiwand.ai is a startup. We work in the field of trustworthy AI, and we actually have a specific focus on fairness and transparency. And we are part of the NoLeFa consortium, which has been mandated by the European Commission to pilot the AI Act union testing facilities. And so these are the facilities that are supposed to support market surveillance authorities in their job of surveilling AI systems that are on the EU market. So let me start and do what a startup always does. I have an amazing new product for you. And this is an AI system that will read a project application, product description, or patent application for you and automatically predict whether this is really an innovation or not. So never, ever read boring hype marketing material again. And independent tests show this tool that I've developed is 99% accurate. And I suppose to metrologists, I don't need to tell you what accuracy is, but maybe I should because we all use the same words to mean different things. So in the machine learning world, accuracy is the number of correct predictions out of all predictions. Okay. So before I move on, just a quick agenda. What am I going to talk about? We will first dive into the nuts and bolts of metrics, and then we will move on to the intricacies of test data. And I hope by the end of the talk, you will at least be amused, and my hope is also understand some of the complexities that lie in the details of testing AI systems. All right, so back to my groundbreaking innovation. That's right, don't invest in it just yet. So accuracy was perhaps not the best metric to measure this system's performance whenever you're in a domain which is highly imbalanced. You might need alternative measures of how well the system is performing. And before I move on, I just want to point out a few things about AI. So under the umbrella term of AI, Martina has already given us a definition, and Thomas has also talked a little bit about the various kinds of AI, but it's really important to understand that AI is very much like when we say mobility, and we mean everything from bicycles to spaceships. So in AI, when we talk about AI systems, a lot of times different people have different things in mind, and I might personally be thinking about traditional machine learning systems that would even include logistic regression, but I'm talking to somebody who's thinking about an agent or at least a chatbot. So it's important to keep in mind how broad of a term AI is as we go through this. So I wanted to look into metrics in different fields and different ways of using them. So here is actually a lovely paper, Ranke et al., Common Limitations of Image Processing Metrics, picture story. And this one demonstrates how you can end up using the wrong metric in medical diagnostics. So what metric you use is an indication of what errors you think are important or not. And in this case, the F1 score ends up picking up the wrong kinds of errors. So what the F1 score is doing is looking at the total area that the image recognition is recognizing. And so in that sense, it thinks prediction 1 or system 1 is performing well. But actually what you want is the system to pick up all segments of interest. And in that sense, the metric is wrong because system 2 is better, and actually the metric that was chosen makes it look like it's performing worse. And I will move on to NLP, and here you will see where my predilection for looking into bias comes in. So I don't know how many of you speak German, but I always find it very entertaining to look into Google Translate or some of the other online translation systems. And by the way, those are actually Gen AI in my world. And see what kinds of funny translations they will give me. So in this case, I asked it to translate into German. My secretary is on paternity leave. And those who know German know that German is a gendered language, and secretary, the male version would be correct if they are on paternity leave, would be Sekretär. And but now it's my female secretary who is on paternity leave. And so as you see, as the tasks get more complicated, the idea of how do you measure an error also becomes more complicated. And just as a further example, let's take a look at one particular metric in natural language processing. BLEU, which is one of the most commonly used metrics. Also, you will, if anybody is active in this field, you will know that it's, even though it's used a lot, it's also controversial. Some of the issues include that it is underspecified. So some examples would be how many reference values. And by reference values, we mean it will compare a machine translation to what is called a correct translation. But since we're talking about language, there could be more than one correct value, and the translation is correct compared against more than one. Here we're getting really into the nitty-gritty of actually machine learning, which is the input sentence is broken down into word tokens and what is the maximum number of word tokens that it will accept. And the problem with an underspecified metric is that every user will input their own numbers, and if that is not made transparent, which actually often it is not possible to compare the test result of one system with the test result of another. What makes things worse is that these metrics are obviously implemented in software, and the implementations themselves differ. One very fundamental step for metric implementation is even what kind of pre-processing is done. So if I have text, I need to prepare it so that it can be processed by the metric and have measurements done. And this pre-processing ends up differing between different systems, and that also influences the value of the metric when something is measured. So what we have in the end is the impression of being able to compare because everybody is using BLEU and everybody gives a BLEU score, but actually the number that comes out varies from system to system that is being compared, and it varies from implementation to implementation. And this makes comparison difficult. This makes reproducibility difficult, and obviously, therefore, verification of results is compromised. And now I'd like to go into also the aspect of bias. And here it's important to remember that these AI systems are used nowadays in very many different fields, and they also include fields of assessing risks associated with people. So here I'm giving an example of an AI system to assess creditworthiness. And the system is supposedly 90% accurate overall. And I've done something which actually most people even forget to do. Break it down, let's say, into age groups. So it's even 90% accurate on the age group 25 to 50 and 90% accurate on the age group 50 plus. But if you investigate closer, you see that the error rates and the errors are different. So looking into the ages 25 to 50, all the errors are false positives. This means that these people receive credit even though actually they are not creditworthy. And the ages 50 plus are false negatives. So these people are rejected for credit even though they actually are creditworthy. Now, there are several issues here, some of them related to the data set, and we will look into that in the next section. So what does it mean for a person to be creditworthy anyway? But what I want to focus on here is that one metric is not enough. Even breaking it down into particular affected groups is not enough. Sometimes you need additional metrics to help you understand the impacts that the system has on different groups of people. Okay, so to summarize, here are some problems that are quite common with metrics and how we choose them. So first of all, the chosen metric does not properly capture what is intended as good performance. And this is really domain and context specific and requires a lot more thought than is often put into this question. Other issues are the definition of the metric itself. So many metrics also have adjustable parameters, and if each user can set their own, reproducibility is at risk. Third, the metric implementation. So when we are testing AI systems, the metrics are implemented in software, and that software itself varies so that running the same test but using different software libraries leads to different results. And finally, when we're talking about metrics and measuring AI system performance, we cannot ignore the fact that the system performance is not uniform over all groups that are involved. And so we need to assess on particular subgroups in order not to miss hidden failures. So we actually need to place some requirements on the metrics themselves. So we're not talking about requirements for the AI systems now. I'm talking about requirements on the metrics that I'm using to assess the AI systems. And we need, first of all, a clear indication of what the metric is measuring, when it can be applied, what its limitations are, and how to interpret the results. The metric needs to be fully specified. Adjustable parameters need to be clearly indicated. And if you use a metric with adjustable parameters, then the values of those adjustable parameters must be documented together with the test results. When it comes to metric implementation, we need standardized software implementations. Alternatively, all tests need to be run using exactly the same software. And as mentioned before, the overall performance is not enough. You also need to assess subgroup performance, and which subgroups are relevant is, again, very context specific. And this issue is known. It is also being worked on at standards level. So I'm giving here a few examples of standards that are going into the nuts and bolts of metrics, how you define them, and when you use them, and also how to be transparent about them. But in order to test an AI system, I need two basic instruments. One is the metric that I'm measuring with. The other one is the test data that I'm using. So let's take a little look at some of the issues that arise in testing AI systems with test data. Here's another example. Suppose an algorithm is to be used for predicting the risk of recidivism for defendants that are up for parole. And suppose it was tested independently by 3 different facilities. Test facility 1 found a precision of 68%. Test facility 2 found a precision of 95%, and test facility 3 found a precision of 99%. Same algorithm, same metric. What is going on? So before I get any questions, there are actually algorithms being used right now that do predict the risk of recidivism. So I'm not making up this kind of AI system. And two, this is purely as an example. So there are not actually 3 test facilities doing this. And I chose the metric of precision because problems with metrics do not rely only on accuracy or recall. There are many metrics involved, and in this case, precision would be one that is relevant and often used in situations like this, because it tells us if you have a label, if a system assigns a label, how likely is that label to be correct? So precision makes sense theoretically in this context. But other than normal variability, how could you end up with such widely differing results among test facilities? And the answer is they were using different sets of test data. And in the first facility, the actual recidivist defendants made up only 10% of the test data. In the second facility, they made up 50%, and in the third facility, 80%. Here's another example. This comes up very often in my work. So imagine an AI system that actually has the following performance for men versus women. The accuracy for men is 90%. The accuracy for women is 70%. Again, these are example numbers, and we know this, but the test facility does not. And suppose that the testing facility uses test data that is not disaggregated by gender. So they have test data, but they have no idea what the percentage of men and women in the test data is. So what overall accuracy would they calculate? Well, if in fact the test data consists of 80% men and 20% women, then the overall accuracy would be 86%. If, however, the test data actually consists of 50% men and 50% women, then the overall accuracy would be 80%. The AI system didn't change. Its actual performance didn't change. only the composition of the test data changed. And I put this example a lot in my talks because this is something I run into very often when doing bias testing. First of all, that I encounter systems that have been tested using data that is not disaggregated, where people have no idea what their, for example, male to female decomposition is. And second of all, when they are informed they need to do the bias testing and they need to disaggregate data into men versus women, and that they need to have test data which is more representative. So, for example, having approximately 50% men, 50% women, all of a sudden the cry goes out, oh no, being fair means my accuracy has deteriorated. And actually, the truth is the accuracy didn't deteriorate. It was always that. They were just measuring it incorrectly. So these two examples should actually also show how important it is for the test data to represent the domain of application where the system is being used. Here's another issue with test data. Sometimes the ground truth isn't quite true. And here I'm going to look into the more recent advances in LLMs. So these large language models claim to be able to do very many tasks. And there has been a proliferation of benchmarks against which these LLMs are tested. And almost as fast as the benchmarks are created, problems with the benchmarks have been popping up. So two examples, one very popular benchmark, MMLU. Actually, the sort of gold standard data itself is incorrect. So when you're measuring a system against a gold standard, which itself is full of errors, it's questionable how reliable your results can be, or even what interpretation to put on the output. Another example is incomplete benchmarks. So there is a benchmark for evaluating how well LLMs synthesize code. And in recent research, they've discovered these benchmarks are incomplete and miss very many kinds of software errors. So again, how reliable are the results on these benchmarks when there are significant gaps in what is being assessed? And a final example referring to bias data. So when we have systems that are assessed against data which is labeled by humans, well, the humans are bringing in their own biases and prejudices when they are doing the labeling. So the final example is about offensive speech detection and how the human annotators bring in biases versus certain dialects into the gold standard labels. And this last problem is a serious problem, especially in the area of large language models and agents. That's because these models are trained on such large amounts of data that it is no longer possible, or it is actually incredibly difficult to make sure that the data that it's being tested on hasn't already been used or partially used in training of the systems. And well, machine learning models, the whole system of understanding how well they work and how well they generalize is based on the idea that the test data has not been seen before. So results of using test data that is already contained in the training of AI systems is highly problematic. And so there are many investigations into how test data, especially benchmark data, has been leaking into the training of LLMs and the impacts this has had on the measurements that come out of benchmark tests. So here's a summary quickly, some problems with test data. It can be not representative of the domain of application, or it contains errors, so that performance results using that test data will not reflect actual system performance when it is deployed. Or there has been leakage from test data into training data or training contexts. So when I say training contexts, it's enough that actually the developers have seen the test data before. In this case, the system will be overfit, and test performance results are inflated with respect to system performance on deployment. And finally, test data does not permit valid statistics on relevant subgroups. So the test data is simply missing some important subgroups that will, however, be affected by the system once it's deployed. So we can therefore also need to place requirements on the test data and on its quality. And for example, it should be representative of the application domain. And this requires a precise definition of the application domain. This is something that Thomas previously mentioned. And actually, they have a very nice paper on how to define the application domain in order to enable random sampling, for example, for creating test data. The second requirement is a complete separation between training and test data. And this includes more transparency on what is contained in training data and methods for assessing when leakage has occurred. And the final requirement would be privacy-preserving secure methods for accessing data on subgroups in order to test for possible bias. And also here, there are some standards being developed to help in solidifying what are the requirements and expectations to put on test data and on how to use that data in testing. And with that, I would like to end here. Thank you very much.
We have to start with the digital calibration certificates. I think that everybody here are tired to listen about DCC, but we have to start. There are people listening online, and possibly one or two don't know what is a DCC. But a calibration certificate is one of the most important product of metrological institute, a laboratory. You have to give the certificate to the clients. And there are other products, but we can start with this. Nowadays, before the pandemics, the majority of certificates are in paper format. In the last years, we take in the paper, put on PDF, and send to the client. Not so much change. It continues to be hard to understand. And there is a proposals, more than one, but there is a proposal, for instance, for some institutes to use a digital calibration certificate, an XML document, easy to be imported and processed by computer machines. I know that there is you can make yourself. You can take, if you are an institute, you can start from zero, doing DCC. But there is a very strong and with a long time work specifications. We can detect these specifications and go on in an XML file. I know that you can put the XML inside the PDF. In my institute, we still do this for the quality system, to not perturb the quality system. But I think we have to consider, take the standards that we have and go on with this in XML format. But the DCC alone is not enough. You have to give meaning for the data. The DCC is a way to format the data. It's syntactics. You have to put the meaning with semantics. Of course, if I take a DCC and a computer system, I know what the data is. If I don't know, I can consult some documentation and program and work with that. But it's hard if you manage not only to put the data, but to put meaning of the data. It's much easier for the one who will get this information. And also, BIPM starts with the SI reference point. SI reference point is the quantities. The objective of their existence is much more than only DCC. Okay. I think the BIPM will have to cope with all the science, all the documentation of science. If you have one quantity, you can go to the BIPM site. It was developed, very strong, very good proposal, implemented. But it's not sufficient for the DCCs. We have to create more ontologies, more semantics to cope with specifically DCCs. And there is some proposals, PTB, NCSLI taxonomy, some domain specifics. There is a lot of proposals. Our goal is in the future, we have harmonized all these proposals and has federated ecosystems of interoperable ontologies. In my case in Brazil, I can translate what I think it's necessary to Portuguese. We have a small, not so large economy. The laboratories in my institute and the secondary laboratories could use our ontology that are that we could put on the INMETRO website. And for our economy, some problems with someone could buy equipment outside with a calibration, could appear some problems, but I think it's manageable. In situations like larger economies like European community, United States, there will be a much diverse situation, and I think that we will have a lot more problems to harmonize these ontologies. And I hope that managed to do this. And with this DCC and ontologies, we are in the heaven. We are now in the Industry 4.0. We can do a lot of things that we cannot do before. The reason that I'm working on this project, we have a collaboration with National Telecommunication Regulatory Body. They have some problems. They have, for instance, thousands of calibration certificates they have to process. Real-time validation is very interesting. When they send their equipment to calibration, they receive, they spend 1 week, an engineer spend 1 week validating the certificate and see if the equipment is good or not to put on to be used on field. This is not the problem. The problem is that the person who is doing this has more or less the same age of ourselves here, and probably will be retired in 5 years. And the government don't hire new people in the same rate of retirement, and the new people have to be trained, and the old people don't trust very well these new people in the lab. So we would like to develop a way to automatically verify the equipment. But if you have a DCC, if you have an ontology working, you can do a lot of things. Removes manual data entry risk. It will be cheaper, reduce costs, and everything is good, more or less. But with this paradise, why it remain low adoption? The first proposal that I see of DCC will be, we'll have a birthday party of 10 years next year. Why there are not so many DCCs issued to clients, not so many services? Because it's complex, difficult to develop the software, okay? And it's not only, I would like to develop a software to read the DCC, I need someone to understand the language, Python, C, or any language that you use, and I need someone to understand metrology, the GAN, the XML, security systems, cryptographic keys, things like that. It's complicated. So it's a chicken egg problem. Labs wait for software, developers wait for the demand. And but many things in the industry take a time to mature before it has large adaptance. I can give you many examples, and I hope that soon we can manage this. And this is a breakthrough. There is a new thing. When the LLMs became popular, some people tried to write a poem with this LLM, and it gives a very good poem, and say, the LLM could write a poem, fantastic. But some people more practical try to work and create software. Software is written text. If you take a Python code, if you take a C code, it's written text. If you take a call of an API, a call of a function, it's a written text. So if the large language model could write the software, write the code, write the API call, even during on the fly, not you put ask and then write the code and then execute the code, and you have your job done. So it became much easier to work with software. They can generate code. They can manage to get the information. Sometimes and this simple insight unlocked the entire agent paradigm. I think all of you listen the word agents, LLM agents, AI agents. This is the idea behind of the agents. You're not asking the LLM to do the job. You ask the LLM, the large language model, to write a code or to write and execute a code to do the job, or a code that calls some functions that do the job. The LLM is quite a bit the control devices. It's the intelligent part of the system. But it's really, we are not asking the LLM to write the DCC or to get the DCC and analyze the DCC. We are asking the LLM to write a code to analyze the DCC. It's good because it's you can verify the code after. You can verify all the functions calls, and it's not inside the complexity of the LLM. You can see what this machine do. So we have the agents. With this idea, you can use LLM like a vibe coding. We test a lot. We take a DCC, ask the LLM to write a code to pick the DCC, the information of the DCC, and put it on the Excel file. Okay. You can do this in minutes. Okay. Easy. But there are some more advanced features like these agents. You have memory, reason. The reason is the LLM. Memory is some kind of file that you keep on your device. Markdown file, many XML file, many ways to write what you have done. You have to not only to write the code, but you have to have an ambient to run that code. And this is the proposal of AI agents. I'm not trying to explain this extensively, but the industry like it a lot, and they tried to sell this a lot. And they create many things that is necessary. MCP, HOA. HOA is a protocol to agents to call to agents. MCP is a protocol to agent to call tools. Tools is an API or something. For instance, the LLM don't know what time is it, so it asks the some place, what time is it, and there is a protocol to make this action. A lot of protocols. This is the two most famous, but not all. Skills is another thing that they create. LLM is a tricky machine. you say, ask to do something, do it you like. If you ask again, it will do another thing. But 5 minutes ago, you do this way, and now you're doing that way. Okay. You say, oh, okay, do this if you like. Write as a skill. This is a small file that say what the LLM do. The next time he will do the same job. Read that file, and I will hope that do the same job. And the orchestration is what the LLM does. It could be very complex agents. We are testing simple ones, but could be very complex agents. And there is a lot of frameworks already created. This one is what we are testing from our project. We start with LangChain LangGraph. LangChain LangGraph, we write a Python code. LangChain LangGraph is some libraries that you put on your Python code, and has these agentic properties. This is the most famous, but there is other with this. OpenClaw is the fashion of the moment. Before 31 of January, almost nobody knows what is OpenClaw. Then it explodes. The creator was hired by OpenAI, but after is an open source agent, assistant. It works like your personal assistant, and you can install on your computer. Okay, you can open the Windows. I suggest to open in the Linux part, Windows Linux system, and you can use this. We are also test, and Manus is a very interesting proprietary solution, web solution. It was bought by Meta and has a very good results nowadays. These three, there are other frameworks. Really, we don't know what's going to be by the end of the year. We have the technology. The technology is developed. The tools that will help this technology is developed. But the way the people will interact with these technologies, if you prefer to use a personal system, prefer to use a Python code with a library, it will be, I don't know. I think that nobody knows. So we suggest using open source systems, at least not fall in a vendor lock-in. At least now, I know that in few years could be a winner, and a winner could be a proprietary system. The majority of people here use Word, PowerPoint, and are happy with that. Some will use LaTeX, but the majority will use this and are happy. So this is the first one is myself. Trying these systems is an old way of doing it. It's hard, but in the future we will continue to have someone to develop. Probably many of us don't have patience. I don't know how it will be, but nowadays you almost have to argue with the LLM to develop something the way that we want. If someone try, know that oh, you don't do correct. And LLM says, oh yes, you are right. I forgot this. But in the future, someone will have to in a bright future, someone have to make the developments, but it will be much cheaper. Something that nowadays we will take weeks to do. We manage now, even now, but the majority of developments will take weeks to do. We can do before the launch, starting now. The development became much easier to develop systems. So, bright future, we have DCC, we have ontology, join, we have an agent, and we can do many things that we cannot do today. This could be the last slide, but it's not the last. Oh no, this one. This is the bright future of reducing measurement uncertainty. Everything's good here. Forecasting service needs, identify drifts of degradation before failure. Everything is good. Okay. This could be now the last slide, but I'm not here to convince you to use agents in your job. I know that if you try, many of us, if you try, the IT department will say, no, we have this large system. You have to keep in with it. AI agents is unsafe. They are ready. It's really unsafe. We're stealing our data, and the people of the IT will say no. And I have a good history to tell. The founder of Google, Sergey Brin, after retired, returned to Google to work with AI. It's fantastic. He's a computer science, I love this. And discovered that inside Google is forbidden to use Gemini to produce vibe coding. He have to go to the CEO and say, I cannot take with these people. You are the CEO, solve this problem. And then he's a billionaire. He managed to write vibe code inside their company. I think nobody here is a billionaire. The IT department will block many of our bright future. But your clients, you are going to use it. Probably not the big clients, but the small clients or clients of a client that is not so big company. We will use this and we will ask for DCC because it's cheap now to open the DCC and make something useful. It's a cultural change, moving from rigid, expensive software projects to agile AI-generated solutions. And for us, I think that there will be some client pressure. By the end of the year, customers will demand machine-readable DCCs to feed their own agents. So we must solve digital data problems now. Last 2 days, we are discussing about the format of data for large numbers. This is the discussions that we have to do these details, because if we make some mistakes here and let it go, agents could use these and in uncontrolled. The problem with the problems is that the problem appears where you don't expect. And so it's hard to make some conformity assessment. You let some information. Metrology has some ambiguity in their definitions. We discussed this in the 2 days before also. But computers don't like ambiguity. Computers want very precise information. Our community is better than lawyers in the community of law, but worse than mathematicians. So we have to work to solve this, taking out some ambiguities, and also have a robust semantic for client consumption and thinking, and agents thinking DCC and this model of work. So for our institutes, I suggest a rapid adoption of DCC, creating and issuing to the clients, because it's essential for the digital ecosystem and enable the customers to build the systems, and also to develop the international metrological vocabularies before it became a nightmare. We have to we should harmonize this and work. I know that the work of BIPM is worse. It's more complicated because it has to cope much more things than DCC, but it's a thing that we have to do. This is the last one.
Good day. I'm Dong-Hun from Korea Testing Laboratory, and I'm going to present the study on the development of a DCC application with AI. Before we go on, let me introduce you 𝐜𝐸𝐿. 𝐜𝐸𝐿 is a public institute established 60 years ago under the Ministry of Trade, Industry, and Resources. Its main job is testing and certification of technological innovation of industries. And specifically, our team is in the Industrial Standards Division, and we are dealing with the calibration, rigor metrology, and reference materials. We have about 100 employees, and we issue about 120,000 certificates every year. So it's a huge number, so we wanted to make a digital service with the data of calibration. So first thing we tried was the quality control. And why is it the quality control? Because we calibrate 120,000 instruments every year. The workload is huge, and we were always interested in the automation. And the automation of manual review of the certificate was one thing we thought about. So the current situation was like this. We were focusing on template inspection and intuitive judgment without data, and sampling inspection was made. We were focusing on the page number mislabeling, font size, or logo image ratio. And why is it that? It was because we didn't have the right data. References are needed to check the data. We need something like past data or similar instrument data. And the administrative pages have similar forms, and so it was stored in database. But the result pages have so various forms, so it was stored as separate files, and it was not in database. So the first thing to do was making a database. And we encountered our first problem that we could not make one extraction tool because there were so many forms. So they had a different number of columns, rows, and sometimes merged cells and multiple tables. So we found that we were using more than 3,000 formats, and it was difficult to make one extraction tool. So at first, we tried the standardization of calibration certificates for easy data extraction. Our approach was proposing of standard templates and layout, which has a minimal number of items with very organized shape. and it didn't work well because of the practical limitations. I'm sorry. I just go on. Okay. So calibration staff didn't want that, and they said that the client will feel discomfort about the new format. And it was true that some different physical quantities have different mandatory information. And finally, if we force them to do this, the data extraction is possible only after the new template application. And so it will take a long time to accumulate the data required for statistical analysis. So we changed our mind and we tried OCR of PDF. We used the table transformer for table object detection and multimodal LLM for OCR and making the JSON file. So we trained an AI model and made a database of 100,000 certificates. And our idea was making the comparison tool. We grouped the calibration results data by similar instrument, which is the same manufacturer and same model. And then we can get some normal data range from the averages. And the idea was that we can now detect whether the IO data is inside or outside of the average range. And so there was a second problem. So we had to group the results according to the manufacturer, model, and serial number. And we found that there was different format for the manufacturer and models. There was someone used the capital letters and small letters, and dash and space, and something like that. So we had developed a similarity search system to find when no exact matches are found. So we have 70,000 instrument data of manufacturer and models from the past data. We clustered them according to the cosine similarities and attached to each label. The most commonly appeared manufacturer name became the label of the cluster. So now we can identify the same instrument even if the label is not exactly the same. So even when the manufacturer name is something a little bit different like this, we can gather it as a group and show our customer the annual calibration history like this. And the next thing we tried was making a data comparison tool. We compared the present result with the similar instrument, which is the result of the same manufacturer and model, and with the same instrument, which is the same manufacturer, model, and serial number. So it gives you the list like this, and here as shown, you can see the yes or no for suspicious typo or suspicious error. If you can click it, you can see the detailed screen like this. So wrapped graph shows that annual data analysis. So it is the example of a talk range, and the present results show some similar trend to the previous ones. And the right graph shows that the blue dot, the present results, is within the guideline. The guidelines are the averages from the similar instrument data, which is in this case is 125 same instrument. And let me show you one more example of micropipette. Okay. So this micropipette has only one data, which means that it is the first time we tested this instrument. And the right graph shows that the lines are lines made from the 484 results of a similar instrument, and the present result is outside the guideline. And we cannot say that it's wrong, but it may be good to check it again. That is the comparison tool we made, and our plan is making this certificate free check service embedded within our system. So usually a calibration step performs calibration, and he prepares the calibration certificate and submit for approval. and the technical manager will review the certificate and make it a final approval. Our plan is making this certificate free check service in between so that the staff and the technical manager can focus on suspicious certificate instead of reviewing everything. And this is something we learned during the process. The first one is that standardization is needed. So reference value and indication values are very common field which appears in most certificates, but we found that sometimes different terminology is used. If you can see this standard weight example, the conventional mass is the reference value in this example, and the nominal mass is the indication value and also the nominal value in this certificate. So the study of ontology or the standardization is needed to solve this. And second thing is that having a nominal value helps a lot in grouping the measurement results to some analytical, to statistical analysis. If you see this flow mirror example, the reference value varies slightly always, and the grouping could be difficult in some cases. And so nominal value estimation is required, and it could be a source of error. So having a nominal value in the certificate is good for grouping the result. Okay. So that was our experience in developing quality control tool for our internal use. And I'm going to share our DCC development experience for customers. So I think it's in transition period that the DCC is mainly for machine reading, but still the human will need to see the certificate. So we made this conversion tool for human customers first. So this is the annual calibration history. And here we provide the customer the PDF converted Excel to them. So this Excel is not our original Excel. It does not contain any equations or raw data in it, but it just shows the result in this form so that our customer can copy and paste it easily. So that was actually some of our customers' requirements. And so some customers are happy about this, but we tried something else, something more like your DCC. This is the calibration certificate extraction tool made by our IT staff using cloud code. So it converts the PDF certificate to JSON, and we can distribute it, the JSON file, through API call, and it can be called from the web browser like this, from the Edge or Chrome. And you can see that we changed LLM here, so the characters are small. So we tried small open source AIs like the Llama 30 billion or GPT-OS SS 30 billion, and both worked well. And we are trying more models to optimize the cost. And this is the flow of this service. So there is an input, calibration certificate, PDF or image, and we process it 3 steps. First one is table transformer. It detects where the table is, so which means where the data is. And secondary, we use text extraction tool. So it extracts the text from the detected area and makes some array. So it converts the image to X, Y value array. Then we use the data structuring using LLM. So it understands the contents and make it some structured JSON. And now we can distribute it through API, like REST API server. And the output can be anything according to the client application, like Excel Visual Basic application or web browser or custom application like ERP or MES. So the right thing is the Excel Visual Basic application example. So if we make this Excel Visual Basic macro, then with one click of the DCC button, you can receive the DCC data from DCC server and insert the data into Excel like this. And if there is a need for human recognition, then it can be displayed in different form for human readable form. And okay, this one is something more realistic example we are trying. So KTR is a customer of Chris. So we are getting our prometer calibrated every year, every 2 years. And now we are reading the PDF or paper of calibration certificate from Chris and insert data into our Excel files like this to calculate the correction factor and annual trend. And we tried this one. So we converted the Chris PDF certificate to JSON file using our extractor and assumed that Chris is providing us DCC through API. Then we can make this Excel Visual Basic application, and we can receive the data from DCC server and insert it into Excel with one click. So this is one example of DCC application if the customer is using Excel like us. And it could be AI, but it wasn't AI this time, but AI will do a great role if it is we are going to make a solution customized for every industry. So we introduced the DCC and Excel conversion to our customer and asked for his opinion. And he said that he needed something else. So this is the instrument setup screenshot of his test equipment. And he was reading the calibration certificate and inserting it into this one. So from the DCC, there is a need to converting the data to this customer's own program format. And I think AI will do a great role in making this custom solution. So we have explained our experience, and let me conclude with our future plans. There are two things. And first one is the reliability. How can you trust AI extract the data? So is it reliable? So it always comes to this question. And it's true that AI does not take a responsibility. And so I think that human should be in the final phase anyway for now. And we are going to try this LLM cross-check. Okay, let me show you this example. So in this case, PDF image is extracted using our tool, but we try multiple LLMs, multiple affordable price, cheap LLMs, and compare the results. And if the results coincide, then it goes to the technical manager for review and approval. And if the results does not coincide each other, then we call the frontier LLM, which is more expensive and slower, but more precise. So something like Gemini 70 billion or GPT-OS 130 billion. So it still will go to the technical manager for review and approval, but I think it will decrease the failure rate of AI, and then AI will be a more better support tool for us to focus our limited resource. And the second thing is the field test. So we are going to cooperate with Chris to make this field example. So Dr. Kang-Eun of Chris has made this gravimetric hydrogen field test standard and made some inter-laboratory comparison tests last year with Japan. And we are going to make this master meter for the verification of hydrogen dispensers for legal metrology. And it needs the traceability, and we need calibration from trace. So our plan is making this DCC and machine-to-machine communication application in the real field in this hydrogen. So details are to be discussed yet, but I think it will be a great milestone in application of the field, application of DCC. And actually, this is the first final slide. And that shows the current state of the calibration service and expectations. And I would like to focus on one thing, that I think that the core value of using AI is that it can make more values from the calibration and the data of the calibration. So the most companies nowadays think that the calibration is a simple cost, and they think that calibration certificate is just a mandatory document to keep in storage box. But with the application of use AI and calibration data, we can make more value and we can change their way of thinking. And to make it, we should keep trying. I think it's the end of my presentation. I would like to thank BIPM for the preparation, and thank you for Chris for the project support, and thank you for your attention. Thank you.
My name is Jeff Gust. I'm with Fluke Corporation. I'm the Chief Corporate Metrologist coming in to you remotely, and I understand I think I stand between you and lunch, so I'll do my best on the presentation today. I'm here to talk about an application that we had kind of went through and what our learnings on developing a particular application of AI, and also I wanted to share some considerations or thoughts, about some of the things that were kind of already presented by the earlier presenters today as well. So let's see, get started. So, some of the inspiration for the journey at my particular company started, our corporation had what we call the Growth and Innovation Conference that, kind of spurs ideas on innovation throughout our operating companies. And we had a speaker by the name of Ethan Mollick, who is from the Wharton Business School, make his presentation on artificial intelligence. And one of the first things he said is that AI has the potential to have a 40% increase in efficiency in the workplace. And as a point of reference, the first industrial revolution increased productivity by 20%. So that's really a shocking, potential for increase in efficiency. And the other quote I always like on that is that, you won't be replaced by AI, but you may be replaced by somebody that knows how to use AI. And again, further motivation for us as well. And the way that I look at this personally is that metrologists are going to use AI in the future like we used calculators in the 1980s and 1990s. It's just going to be another tool to make us more efficient in what we do. So our process for ideation on this is we hosted an AI workshop where we brought in some AI experts and we brought in some subject matter experts, and we kind of went through a day in the life of a metrologist. And one of the main documents that we reviewed for that was ISO 17025, where we reviewed every requirement of 17025 to think about any potential place where AI could make the workflow better for people to comply with this document as well. And from that, we segmented the ideas into the following categories to start, organizing it. And then after that, we further developed our ideas by creating affinity diagrams. So we understood that there was applications in interval analysis, chatbots, risk analysis, backlog management. You could see the whole list of possibilities that we went through in this particular workshop as well. And then from that, we organized all of our ideas onto a 2x2 matrix so that we could look at the highest impact and the easiest to implement ideas. And from that, we could start building business cases and also to evaluate our data availability, because you really can't apply AI unless you have a good data set, like our previous speaker showed. If you don't have a great set of data to start with, that's pretty clean and appropriate, there's not a lot you can do. So, and as you can see, kind of in the upper right-hand corner there, it's kind of small on the slide, but vision technology was one of the top idea that came out of this particular workshop. So simply the concept that we were starting to investigate is, can we build an innovative AI-based product which will automate calibrations for equipment that's not interfaceable? And as everybody knows, there are tens of thousands of instruments, test and measurement instruments out there that get calibrated every year that have absolutely no interface. And, mechanical pressure gauges, dial indicators, digital multimeters without interfaces. And the calibration workflow for those all requires a human being to stare at the display and enter in the data manually. And we thought that if we can automate this process, then we could improve quality and reduce keystroke through the reduction of keystroke errors, possibly reducing calibration time. But again, the real goal on that is no training for individual readouts required. And to kind of expound on that a little bit, that there, long before AI came around, there was OCR technologies out there. But OCR technologies came with its fair share of challenges as well. As you could kind of see on this display, what are the last three digits on this particular readout for this frequency counter? So OCR definitely has problems if there's challenges with image quality or font variations or complex layouts, special characters, and all of those equate into accuracy issues of OCR technology. And typically for an OCR technology, it requires hours of training for a single individual display to be able to start interpreting data properly. And if the lighting changes or the display, if the camera is bumped a little bit, you may have to start the entire training process over. So it really doesn't wind up being a very efficient process for you to utilize OCR technology in its previous forms. So, what makes this idea different? Our goals are that we wanted to be able to read any digital display without any training whatsoever, that we could put any display in front of this camera and it would automatically interpret and get you the correct value. That it wouldn't be sensitive to position. It wouldn't be sensitive to orientation. It would be able to read different colors and different font sizes as well. Mechanical gauges or electronic gauges. Then there's some subtleties about detecting where the actual negative sign may be in a digital readout as well. Is it right next to the number, or is it on the far left-hand side of the display? And in addition to digital readouts, we wanted to be able to read what we refer to as round gauges, analog meters, and there are hundreds of different types of varieties of those as well. Pressure gauges, temperature gauges, torque meters, panel gauges, so that have an analog type meter movement as well. And we wanted to be able to do all of this without a special camera, that you can fundamentally use any kind of a webcam. So we took to developing the tools, and I could say that our software team was really engaged about this product or this project as well. Before this was really a fully funded or formed project, most of this was done, after hours, when we could sneak in work to be able to do this when our usual assignments were done for the day. But again, it created a lot of engagement from our development team. They would often, some of our development team were on the other side of the world from where we were at, and they would call us sometimes at 2 in the morning their time to to share with us a breakthrough that they might have had. That they've been working hours on this idea as well. And their initial proof of concept showed that we were getting some really good results out of that. And one of the interesting things that we never expected out of this is the AI also gave us some additional context on these readouts that we never anticipated. So for example, on this display, not only did it say that the reading was 0.0, it said, oh, you're on the DC voltage range reading millivolts. And I see that you are not in auto range, but you're locked in on the 6 millivolt, the 600 millivolt range. And this device is a Fluke 87.5 true RMS multimeter. We were really surprised with the information that the AI was returning back to us on context of this device too. So that was a pleasant surprise. So we brought this forward and into an innovation week where we were doing demonstrations for senior leadership in the company. And at that time, we determined that it was not ready for prime time, that when we really started looking at the process, there were significant accuracy issues with this technology as well. That if there were glare or reflections on the device, that we were having trouble with that, or like this photo shows, if the segments on the display have any degradation, we were having a hard time interpreting that data as well. And as we were developing this technology, we actually we kind of hit the wall for the limitations on current versions of some of the AI engines. And there were a couple of instances in this project where we literally had to wait for the next generation of a technology to be released so we could start back up with some of our work. And one of the things that one of our mistakes that we had learned on that is that the team had not quantitatively evaluated image accuracy. And we hadn't defined what good looked like for that process, what an acceptable result would be. So as a AI developer and programmer, they got it to work 1 out of 10 times, or maybe 5 out of 10 times. They thought, wow, this is a smashing success. When a metrologist looked at the results and said it was inaccurate 5 out of 10 times, they said it was a horrible failure. There was a real key communication disconnect between the teams on that. So we had to do some pivoting, in this process. And one of the things we had to do was to establish a definition for metrological accuracy for the image capture process. And when we developed that, we started looking at the measurement decision risk models similar to what's in JCGM 106. When you make a measurement in a calibration and you want to know if that measurement is actually in tolerance or out of tolerance because of your uncertainty, the best values that I've seen out there is typically a false accept risk of 1%. So the possibility that you're saying that something is good when it's not really good is that 1%. And so we decided to use that as a metric, in this process as well. And from that, we significantly ramped up our picture collection and training for the model as well. And again, we have developed a fairly successful tool. I'm not here to talk about it right now, but I wanted to really share some of our learnings out of that process. And the couple of things that we observed as well is this isn't just a metrology application. This can be used for a lot of other applications for condition monitoring in factories or in dangerous locations where it may be too dangerous to have a human being. You might be able to set up and you don't have an IIoT device installed in that location yet. This might be a very cheap and easy alternative method for this process. And the biggest learning out of this is that anything in AI is definitely a 2-step forward, one step back learning model. Just when you think you've got things working well, you don't, and you have to go back and reset and progress forward. So with that, I'm going to kind of do a transition to some other thoughts as well. And as we look at AI that is coming out, we started evaluating different parts of 17025 to think about what are the risks or considerations when we put together AI models around different parts of ISO 17025. So section 4.1 for impartiality. And I think Rania did a really nice job of discussing bias and concerns with impartiality out of that. But we need to make sure that our models, data sets, and prompts are avoiding those type of biases. And I think we're going to need to look to our data scientist friends to be able to help us to do that. But we have to be objective, but this has to be supported by human verified results. In order to ensure that we are treating people impartially, I think we have to have humans in the loop still. And again, that avoiding of prompt-induced bias or conflicts of interest definitely needs to have some sort of measurable process. And again, as I said, human in the loop in here as well. Confidentiality. If any data that's collected during the test or calibration process, we need to make sure we're protecting customer information. That any information that are being fed into larger models have to be anonymized as well. Removing any kind of personally identifiable information to meet European and other nations' regulations for this as well. And even on things like digital pictures, those have to be cleaned of the metadata, like in the EXIF information that might have GPS location, dated time. In that metadata, you need to make sure that those photos are going to be purged of all that kind of information as well that are going to be used in these processes. For section 7, ensuring validity of results for our measurements, that's, I think, where we're going to have to spend the biggest amount of time for AI applications. We are metrologists that we are assuring measurement quality out of this process, and we need to have a human verified data set with which we can use a comparison set to evaluate the accuracy of our models, and probably repeatability and reproducibility type of evaluations on that as well. And again, going back and keeping that set is a standard data set. You should have, so for an example, with our AI application for the optical imaging technology, we have a set of 1,000 different pictures of different displays and readings that have been human verified, and we keep that set off to the side. We don't use it for training. We use it as a test tool where we will go back and test the model periodically against that data set to understand if we are improving the model or if we are getting shifts that would change previously correct results as well. And then, under section 7.11 for control of data and information management, we're going to have to ensure that we're protecting this information from unauthorized use, that we can safeguard it against tampering and loss, because a lot of these systems now are using things like Amazon Web Servers, out there, which is a great company, and not calling them out is a negative part, but more and more people are using cloud-based data storage. So how secure and how reliable and how dependable are those cloud-based storages and retrievable, in case of a loss, and of course, maintaining integrity of the data is a big concern for this as well. So I just have a few more thoughts that kind of, again, fit into some of the things like that Rodolfo had said as well. So a few last thoughts about AI is, can AI write automated calibration procedures? Can it do uncertainty analysis? Can it be a knowledge retention tool? Can we review scopes of accreditation and calibration certificates? And I think the answer to all of those is, yeah, probably. I think that we can solve a lot of problems. And a lot of our presentations have been about what possibly can it do. And yeah, I think that we can succeed. We've seen, like the previous examples, a nice application of success, as well. But, these, the possibilities for AI in metrology are probably unlimited. There's so many things we could do. You saw, at the first part of this presentation, all the different categories and all the different possibilities where we can apply AI. But, and again, I think that, as it was explained earlier by our previous presenters, particularly I think Martina had brought to light the concern that for AI to really work for us, we're going to have to teach AI core fundamentals. We need to teach it to understand 17025. It's going to need to contextually understand the GUM and the VIM. It's going to need to be able to look at manufacturer specifications and to be able to interpret levels of confidence for associated instrumental measurement uncertainty as well. So there's a lot of sensitivity out of that. And again, as Martina had stated, when we talked about uncertain, we use the term uncertainty. She's like, well, I'm not sure if your uncertainty is what we think about uncertainty. Are we talking about the same definition? A lot of these things, a lot of the AI has been developed, has not been developed with the metrologist in mind. It's been developed with computer programmers and developers and other industries in mind. So we're really going to need to teach AI metrology from our vernacular and context as well, and which is quite different from a lot of society. And I'm going to use one that is, yes, it's kind of a one for associated with imperial measurements, but if an electrical metrologist uses the word 1/10, they usually mean a decimal point 0.1. Yeah. Now, if you said to a dimensional metrologist that it's that they said it's 1/10, usually they mean it's a tenth of a thousandth of an inch, in that, and that's a very common term for dimensional metrologies in that context. So understanding who you're speaking to, just like the M layer is currently being developed to understand if you say 25 degrees on a digital calibration certificate, are we talking Celsius or are we talking phase angle? It can be, 25 degrees can be quite different things. And lastly, we're going to have to codify 150 years of metrology knowledge and insight into AI before we can really realize a maximum benefit.